Honey, I didn't even know what that was. But it was second, so purple was first. Okay, lesson 29. Lesson 29, uniform motion problems. Like I mentioned a little bit ago, this book, for whatever reason, splits up uniform motion into several lessons. What I like to do is I like to teach the uniform motion problems one way, and that's it. So regardless of what it looks, what type of problem it is, and sarcastic everyone, if you do all these problems, you can use the same steps to solve them. First of all, and I'm summarizing my steps here, always start with the distances. So let's jump right into an example here. Example 29.1. Napoleon walked part of the 60 miles to the site of the battle and rode the rest of the way on a caisson. Technically, you don't have to draw a diagram, but most of the time it really helps. So let's do that. We have Napoleon. What does it say? He walked part of the way, and then he rode the rest of the way. So this is what it looks like. He started here. He went. He walked, and then he rode. And we always start with what?
The distance.
Distance.
The distance.
And it says that he walked and then he rode. What distance number do we have in that example? You should all be on page 132, example 29.1. What distance do we have? I'll give you a hint. The units will be in terms of distance, okay? Miles per hour would be rate or speed.
That's distance. Miles.
Miles would be the distance. What do we know about distance?
It's far.
Yes.
It's in walking distance.
No.
Half of it.
All right, let's try this again. Stop. Napoleon walked part of the 60 miles to the site of the battle and rode the rest of the way on a caisson.
Miles.
Miles is the units, right? And that's the right type of units. We're looking for distance. Let me spell it out for you. Distance. Okay, so we always want to start having some kind of equation expressing our distance.
60
We have
miles.
60 miles, okay? What does 60 miles represent? What do we do with 60 miles?
It's the entire length, so when we put walking
Okay.
and road together, it equals.
So this whole distance is 60 miles.
Yes.
So walking plus riding equals.
So our distance walking plus our distance riding is 60 miles.
Can you do W plus R? It's just so much
That's
easier.
what I do.
I don't like the
Walking and riding?
The D just.
Okay. Are you talking about the distance he walked, or the rate that he walked, or the time that he walked?
The first.
How are you going to tell them apart?
It's the first one I write down.
Oh. So distance gets to be W, whereas the rate that he walked gets to be R?
No.
Okay.
No. It's W plus R equals 60.
Okay.
And since you always start with distances, I know that the first equation I write down is distances.
Okay. So in your problem, W means the distance that he walked?
Yeah.
Okay. What do you use for the rate that he walked at?
I don't really get these problems out.
So you're trying to tell me what you
W.
do.
It's W. It's W.
W?
Yeah.
W is the rate that he walked at? Okay, so in this equation, W is the distance that he walked, and in this next equation, W is going to be the rate that he walked?
Yes.
Okay. What about the time that he walked? Is that also W? Do you think that might be confusing?
3W.
I think that DW plus DR is more confusing. Like to me.
What does DW represent?
The distance walking.
Is that obvious?
Yeah, but for
Okay,
some reason
okay,
it confuses
thank you.
me like a
What?
lot.
Okay, well, get used to it. Walking to algebra 2.
Well, I could get used to the other way. That's less confusing.
No, you can't. All right.
Okay.
Unless you completely understand it and you have no trouble with these problems and you can solve them and get them right on your own, do it my way. How's that?
Okay.
Glad we're on the same page. So step 1, start with the distance. Step 2.
Blue.
Step 2, replace your distance with rate times time. So if this is our distance walking, we're going to replace the distance with rate times time. And it's rate walking times time walking. Distance riding, we're going to replace that with rate times time, and that's the rate riding and the time riding.
Oh.
This is why we use these kinds of variables. We know that this is the rate walking. It's very, very clear what it is that we're talking about. So all I did is I just replaced distance with rate times time, because we know that rate times time equals distance. So we have distance equals rate times time, distance equals rate times time, and when we add these two, we get 60.
So confused. I get it.
Okay, we've got quite the range of reactions right there. So confusing, and they get it. Just follow along. This is why I write these things out like this. Is so that if you don't feel like you get it, follow the steps, and you should accomplish the problem, and eventually you will feel like you get it. So just smile and nod and follow along, and we'll go from there.
Blue, girl.
We already done blue and purple, so.
Green.
Nope. Okay. Step 3, plug in what you know. Plug in, I'll just call them givens. What are we given in this problem? It says he walked at 3 miles per hour.
And rode at 9.
So he walked at 3 miles per hour. What type of unit is that?
Rate.
Rate, time, or distance?
Rate.
Rate. So that's the rate that he walked. So rate walked is 3 miles per hour.
And the rate rode is 9.
And then he says he rode at 9 miles per hour. So that's the rate that he rode is 9. Now notice what I'm doing here. I set up my equation, and my next step, I'm putting everything right. I'm lining things up, and I'm doing the same thing here. I put a 3 in the same spot where the rate walking is. I put the 9 in the spot for the rate riding. I've got a plus sign there. I've got equals 60.
Wait.
Now I just need something with something for TW and TR. And
It could be 5 and 1.
I'm not done with this step yet. And then keep reading the problem. It says, if the total time of the trip was 8 hours, for how long did he walk? Now, did it tell us the time that he walked?
No.
Did it tell us the time that he rode?
No.
What did it tell us?
The total time.
The total of the two. So that's where step 4 comes in here, is any other relationships, like total time, if he went, sometimes it'll tell you like the total time. Sometimes it'll say
Twice
that
as fast.
he rode twice as fast as he walked, or so-and-so was driving 20 miles per hour faster than the other person. Whatever the relationship is, for anything that it doesn't flat out tell you, like these two numbers, you have to get another equation to express that relationship. Yes.
But they'd always give you another equation, right, to solve it?
Well, they either have to give you something or give you a relationship or something.
Purple. Green. Brown.
So step 4 here is to write equations for any other relationships. Equations for other relationships. So in this case, and I'm going to put this off to the side, it told us that the total time was 8 hours. So that means however much time he spent walking plus however time he spent riding, that total is 8 hours. So now I have to do something with this equation because I've got 2 spots to work with.
Why?
So I need to solve this for one of the variables so that I can plug it in. Yes?
Who cares how far we walked?
People taking this math class. Alright, so, since you apparently care, or if you don't, you should, pick one, TW or TR.
W.
Okay, so let's say that TW equals,
Big W.
what's TW going to equal?
It's going to equal 8 minus TR.
8 minus TR. So TW goes right here, so TW equals 8 minus TR.
Wait, I have a question.
Yes?
Does that mean TR equals 8 minus TW also?
Yes. You can do it either way. That's why I
It
asked.
doesn't matter. Okay. Well, no,
Now,
can you,
whichever way you do it, if I took this and solved for this variable,
but both
and I plugged should I make this green or blue?
Blue.
Blue?
Purple.
I think it's blue. Because it's just carried over from the
And
previous
the other
equation.
TR.
Now, so this TR didn't, I just left there
Oh, okay.
because I substituted for TW, I put in 8 minus TR for TW. And now by leaving this TR just as a TR, I now have one equation with only one variable, TR.
Yay.
And now I can solve.
I don't know if it takes
let's
that
see.
long to
Brown.
solve.
step 5, solve for a variable.
We should have
It is
all
actually a
colors
cool
on the
color.
board at the same time.
So solve for a variable, it's okay, I gotta distribute this because there's parentheses. 24 minus 3 tr, because we're distributing, plus 9 tr equals 60. And we've got
Now you
6
do
tr,
another
subtract 24 from both sides, we've got 36, I agree, and tr equals 6.
Yay!
6 what?
Oh, TR.
Hours.
What does the T stand for?
Mile.
Therefore, it needs to be
Miles per hour.
So hours.
Hours.
Right? We solved for a time.
So what do we get?
Now we're not quite done.
Okay.
Let's go with black because because step 5 is to solve for an unknown variable, but then step 6, our last step, is check the question. What is it asking for? Because sometimes what you solve for is what the question is asking for. Sometimes you have to use this answer to answer the question.
I know.
So the question here
what
is the question here is for how long did he walk? So what variable is it asking for?
PR.
them together.
We solved for TR. It says for how long did he walk?
Really?
So the question is asking for TW. It's the time that he walked.
Yeah.
So even though we solved for a variable, we're not quite done because we drew our diagram, we set up our equations, we plugged stuff in, we solved for a variable. And it was a great time to stop and see what the question is asking for. And it's asking for how long did he walk, is asking for TW. Let's see, so we have TR. Here's the relationship with TR and TW. TW, which is what the question is ultimately asking for, is 8 minus TR. And TR, we just figured out, is 6.
Would it have been better if you solved for TW instead of TR?
Certainly could have.
Well, no, would it have been better so then you wouldn't have.
It would have been slightly shorter, slightly more efficient.
No.
I just wasn't looking ahead that way.
Alright.
So then TW equals 2. Am I done?
Yes.
No.
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 Because you still have
This is a word problem. Make sure that you have your units, whatever the units are.
2 hours.
Are you sure?
Yes, because it's the time.
That's right, it's time. And that's why we use dr and t, distance, rate, and time. So if the variable that we solve for is t something, we know that our units need to be something in terms of time. Hours, minutes, seconds, like that. And in this problem, it talks about hours, so our answer to the question is 2 hours.
There's some that are in seconds.
Possibly. Most of them are in hours. Every now and then they'll give you a problem that might have minutes or seconds, but most of them are in hours. Let's see. I'm not going to walk through the whole thing on the other examples, but I do want to set them up for you so you get an idea of how to get started. Because once you draw your diagram, get your distance equation, and then change to here, the rest of the steps are all the same. You plug in what you know, and you set up things for whatever you don't. Yes?
How is there going to be other problems?
Well, that's my point. The only thing that's different from this problem than what we've done previously is that in this case, one distance plus the other distance equals a number. In the problems that you've been doing, it's this distance equals that distance.
Okay.
That's my point. That's my whole point in having one way to solve it. They're really not that different. Question, will get the next one ready?
Yeah. Is that all for the first lesson?
That's the whole concept. There's 2 more examples, and I just want to get started so you see those. And I want to do a couple other examples so you have seen that. Okay, 29.2. Longshanks, PW. 54 miles apart. No. Edward began the journey to the meeting place, and the Queen set out to meet him. So what do we got here? We've got Edward Longshanks is heading this direction, and Queen Eleanor is going to meet him. I drew a diagram of what's going on with the distances. And it says that they were 54 miles apart. So that means the total distance here is 54 miles. So we have, what's my equation that talks about the distances? I'll give you a hint.
D.
Oh.
Longshanks
It's like
and Eleanor.
It's like RETE time plus RLTL equals 54.
Isn't it just?
Yes, but you're trying to do the first two steps at
together,
once.
you get 15.
The two distances, so you were already jumping ahead to the next step of replacing distance with rate times time. The two distances add up to 54 miles. And one thing I need to point out on this problem here is that this one says that Edward began at 8 a.m. 2 hours later, the Queen set out to meet him, and they met at 4 p.m. So when it gives you clock times like that, you have to convert them into how much time has gone by. Because the time spent walking, you have to say how many hours. Right? You can't just say, how long was he walking? 8 o'clock. That doesn't answer the question. Longshanks starts at 8 a.m. 8 a.m. and he starts going that way. Queen Eleanor starts 2 hours later. What time was it when she started?
10.
10 a.m. She starts going, and they meet at what time?
12.
4 p.m.
4 p.m. Therefore, what is Longshanks' time? How long was he traveling?
6.
No,
No.
I'm tired.
What?
8.
8 hours. 8 to 12, right? 8 to noon is 4 hours, and then 4 hours after that. So Longshanks' time was 8 hours, from 8 a.m. to 4 p.m. What's Queen Eleanor's time?
6.
6. 10 a.m. to 4 p.m. is 6 hours.
Then you have to do R and T.
Yeah, and then you just follow the rest of the steps. Let's see, 29.3. Like I said, I just want to set some things up here because I think you guys can get it from there. At noon, Rocketman whizzed off to Rocketman in the opposite direction, and then after a certain amount of time, they are 11,800 kilometers apart. So in this case, there's two people starting at the same location. Rocketman goes one direction, and the other person goes the other opposite direction. And after a certain amount of time, the distance apart is 11,800 kilometers. By the way, notice that they throw in different units sometimes.
You.
In this case, it's kilometers.
Metric.
Usually it's miles, but they will throw both at you just so you get comfortable working with them either way. Okay, so we got Rocketman, Moonfo. What's the relationship of the distances?
DR plus DM equals 11 something.
RTR plus RMDM equals
Yep.
11.
That's the next step, and we go plugging stuff in. Now, like this example, this one also has clock times. It says at noon. I'm putting this in green so that you know that we're talking about the equations for other relationships like time. For Rocketman, he leaves at noon, 12 p.m. And at the end of the time we're measuring here, or let's see, at noon he takes off that way. At 1 p.m. or at 1 hour later, the other one goes the other direction. So this one's at this is at 1 p.m. And then they are that distance apart at 5 p.m. 5 p.m. 5 p.m. What is Rocketman's time?
5.
5 hours, from noon to 5 p.m. What's the other guy's time? 4 hours. From 1 p.m. to 5 p.m. is 4 hours.